The formal definition of Newton's second law is as follows. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the objects. This principle derives the equation F is equal to ma, or force is equal to mass times acceleration. To conduct our experiment, we did 5 trials of dropping different masses of water bottles to determine the time it takes for the force of gravity to pull the bottle 1 meter. Using conservation of energy, our theoretical calculation showed that no matter what the mass is, the bottle would fall 1 meter in about 0.45 seconds. With our experiment, we collected data for an average of 0.46 seconds of fall time, which matches up quite accurately with a theoretical calculation of 0.45 seconds.
Newton's second law states that the force is equal to the mass times the acceleration of an object. Now, from the gravity equation, we also know that the force of gravity is equal to the gravitational constant times the product of the masses of 2 objects over the distance between them. In this case, the first mass is the mass of the Earth. The second mass is the mass of the water bottle. The distance between the two is more or less the radius of the Earth. There's a 1 meter difference between the radius of the Earth and our radius, but that's negligible. Kinematics tells us that 1/2 times the acceleration of an object times the square of the time that object takes is equal to the displacement. If we solve for acceleration from the kinematic equation and substitute in the expression for acceleration and set it equal to the gravitational force equation, we end up with gravitational constant times the product of the 2 masses over the square of the distance is equal to the mass of the water bottle times 2 times its displacement over the square of the time. This can be rearranged to gravitational constant times the mass of the Earth times time over the distance between the 2 squared becomes equal to 2 times the displacement. Now, the gravitational constant is 6.67 times 10 to the negative 11th. The mass of the Earth is 5.972 times 10 to the 24th kilograms. The radius of the Earth is 6.371 times 10 to the 6th meters. The average time the water bottle took to fall was 0.46 seconds, and the displacement of the water bottle was held constant at 1 meter. Plugging all these values into our equation, we return an experimental value of 2.0766, whereas our expected value was 2. Therefore, our percent error, observed value minus expected value over expected value, is 3.83%. Therefore, our trials modeled Newton's second law within 3.83%.
An application of the Newton's second law is to the rocket launch. For a launch, you need a propulsive force, and this force can be altered by either increasing or decreasing the mass of the rocket. Looking at the Newton's second law equation of F equals to ma, we see that A is equals to F divided by m. So if we decrease the mass, we increase the acceleration. If you increase the mass, then you decrease the acceleration. Looking at this video about rocket launch, we see that the propulsive force comes from the burning of the gases. And from A equals to F over m, we see that in order to be able to obtain the launch, the ratio of F and m needs to be greater than the acceleration due to gravity.